The original equation? Yes? Hey, no? Oh, that's fine. I can look at that. All right, so yeah, you get a horizontal tangent line has a slope of 0, so you get your derivative, set it equal to 0, solve. Once you get your solution, set that back into the original equation or the original function, and you can get your points where the tangent line is 0 to the curve. Tangent line is horizontal line. All right, so that we don't do nothing, and since some of you will be absent tomorrow, so that you won't get to see some of this tomorrow because you won't be here, we'll go through like a mini lesson of extending what we've done with implicit differentiation so far. So on Friday, we got introduced to the idea of implicit differentiation, and all the rules are the same from before. So power rule is still the same, and quotient rule is still the same, and we'll eventually run into it, and chain rule is still the same, and product rule is still the same. All the rules are still the same. The only new thing is that when you differentiate a y thing, you get a dy dx, right? The way it works with like writing equations of tangent lines to the curve at a point, still the same. So like everything that we've done is the same. The only new thing is differentiate y, get a dy dx. So we'll run through an example here where we just kind of have a fairly basic equation to work with. You know what, maybe we'll do one other example besides what's up here so we can see a second derivative. And then we'll get into a couple of chain rule type problems as well. Yes, sir?
dy dx, that's the same as f prime.
Yeah, so dy dx is a more generic version of like f prime of x. When you're dealing with f prime of x, that's because you have a function notation, f of x equals something. When you have something like this, that you can't really write in function notation, then you have to fall back on like y prime or dy dx instead. And I prefer dy dx because y prime is too easy to like slowly morph into y over the course of several steps by accident. So, just finding the derivative of this function, what does x squared turn into? And what does 4y squared turn into? 8y, and then you differentiated a y thing, so you slap a dy dx on there. And the derivative of 4 is 0, so don't forget to zero out the constant term. Then you might want to isolate your dy dx. So you have dy dx equals, what would we have when we isolate this guy? So what would we do first with the 2x? Minus it. And then what would we do with the 8y? Divide it. And then you could go ahead and like simplify this. What does the fraction simplify down to? Negative x over 4y. So you end up with, that's your derivative. So that's just kind of just straight off of what we did on Friday. By the way, what's the shape that this thing makes? You guys remember that from pre-calc?
Oh, it's a circle.
Sort of. Ellipse, yeah. So if it were a circle, the x squared and y squared would have exactly the same coefficient. Since they don't, but they're both positive, we know that this is an ellipse. So a circle, it's just, it's a squashed circle. Yes? A parabola would look like this, but only one of the variables would get squared. So parabola, either x squared is squared or y is squared, but not both. An ellipse, they're both squared and they have the same sign. A circle, they're both squared and they have exactly the same coefficient. And a hyperbola, they're both squared and they have opposite signs. So one's positive and one's negative. An ellipse is just fancy talk for it's an oval. So you have your derivative. Now we're giving you a specific point, root 2 comma negative 1 over root 2. So let's plug that in here and say, all right, slope m equals the derivative at root 2 comma negative 1 over root 2. And then you plug stuff in. So negative x is going to be negative root 2 over 4y is 4 times negative 1 over root 2. And then we want to clean that up because yuck.
Wait, where's the root 2? Where did that come from? Oh.
So x, y So let's multiply out the denominator. And what do we get down there? Negative 4 over root 2. And then do you like divided by fractions? I don't like dividing by fractions. So instead of dividing by fractions, you can turn this into multiplication. So rewrite this as negative root 2 times what? Root 2 over negative 4, or negative root 2 over 4. And then this works out more nicely because what's root 2 times root 2? Just regular 2. So we have negative 2 over negative 4. And so the slope turns out to be a nice 1/2. Ta-da! So if you wanted to write the equation of your tangent line to that ellipse at that nasty point, you'd have your slope 1/2. And now you've already got the full point. We have to give you the entire point most of the time with these implicitly defined curves. Because if we only give you the x, finding the y here wouldn't be so bad, but often the y would be terrible to solve. Yes?
How did you get the negative 4?
Here?
The whole number. In the second part. Right under that. Right? No. Negative 2 over negative 4.
Yeah.
Here?
No,
Under.
Here.
Yeah.
Hey!
Yes. How did you get that?
From there.
Yeah, but like.
I copied it. So I have negative root 2 times root 2 is negative 2 on the numerator over the negative 4.
Oh, okay.
If you, like, when you turn this into multiplication, have the negatives follow the root 2, then the negative times the negative is a positive 2 over positive 4, and you end up in the same place. So now that you've got your point and you got your slope, put them together. You got y minus the y coordinate, so y plus 1 over root 2 equals your slope times the quantity x minus the x coordinate, so x minus root 2, and you can just leave it like that. You don't need to isolate y, you don't need to distribute the 1/2 and then like subtract the 1 over root 2 over. You just call it a day, and that's fine. So that's, nothing different from before. The only new thing is differentiating y gives you a dy dx in your work, and then you got to isolate that to get your derivative. Any comments or questions to follow up on example 4? All right, let's extend it. So we've got our derivative, and we want to know where's the tangent line horizontal, so what do we do with our derivative to find points where the tangent line is horizontal? So that what equal to 0? Not the tangent line. What do we set equal to 0? No? Maybe I shouldn't have used the word if.
Initial function.
Derivative. Some of you said that. I ignored you. All right, so the derivative. Set the derivative equal to 0. So you want, where's the tangent line horizontal? Set the derivative equal to 0. You got your derivative is negative x over 4y equals 0. And you solve that. What do you get for a solution? Who equals 0? X equals, because we do have two variables now. We have an x and a y. So you multiply the 4y over, 0 kills it, and you get x equals 0. Is that a point? No. So what do we do with that solution? Plug it back into the initial equation, or in the initial function. In this case, not a function equation, but whatever. We know what you mean. So you plug that back into the original equation. So you have 0 squared plus 4y squared equals 4. So y squared equals 1. And so what's your y equal? Plus or minus 1. Because it's an ellipse or an oval, how many places on an oval are you going to have the curve be flat? Twice, right at the top and at the bottom. So it makes sense. If you recognize, oh, that thing makes an ellipse, it makes you kind of a little bit easier to answer these kind of questions. All right, in ellipse, there's a top, there's a bottom at the top, and at the bottom, the curve is flat. So that's where I need 2 points where the tangent line is horizontal. So you put this together, and you have 2 points at 0, comma, plus or minus 1. So once you got your equation for the derivative, set it equal to 0 to find out where the tangent line is horizontal. Solve whatever your solution is, plug back into the original equation, and solve for the other variable, and you're done. If we want to know where the tangent line is vertical, what happens with your slope when the tangent line is vertical? It's undefined. So in your derivative, how can we make our derivative be undefined? Yeah, divide it by 0. So we just set the denominator equal to 0. So what was it? dy dx was what? Negative x over 4y? So this is undefined if 4y equals 0. Right? So if you want to know when is the derivative undefined, because that's when the tangent line is vertical, just take the denominator only from the derivative and set just the denominator equal to 0 and solve. So you'd have y equals 0 as well. And then you do the same thing to get your point. So once you got your solution for one of your variables, plug them back into your original equation and find out the solution for the other point. So you have x squared equals 4, so x equals plus or minus 2. So you'd have plus or minus 2 comma 0. So you'd have 2 points where the tangent line is horizontal on this ellipse and 2 points where the tangent line is vertical. And I think we've now kind of almost done as much with that as we're probably going to. Now we can do one more thing. So let's continue on with it. Before we do you guys have any questions with everything that we've done so far with that ellipse? One more thing we can do is get the second derivative. So it's just like before. We don't have to stop at the first derivative. We can keep going. So example 5 more. Get the second derivative, d squared y over dx squared. So in order to get the second derivative, what do you need to have first? The first derivative. We already got the first derivative over there, so let's just copy that down. What's dy dx equal? Negative x over 4y. So there's no reason to redo that. We already found it. So now we just pick up where we leave off and get this guy's derivative to get to the second derivative. So when we differentiate dy dx, we get the second derivative, d squared y over dx squared. So differentiate the left side, and boom, you got your second derivative. Done. With the left side. And then you come over here, and what rule do we have to use to differentiate negative x over 4y? The quotient rule, because it's a quotient. So you look at this, hey, it's a fraction. Hooray, quotient rule time. Woo. So low for y. D high is what? Minus high, negative x. D low is 4 dy dx. Watch out, the rule still applies of if you differentiate a y thing, slap a dy dx on it. So when you do d low, derivative of 4y is 4. You differentiated a y, slap a dy dx on that 4. All over low low. So low low is take the 4y and square. Now, cleaning this up is fun. We want the derivative in terms of x and y. So we want the second derivative, to be totally dependent on x and y. Right now, it's dependent on x and y and dy dx. So, what do you know about dy dx? What is it the same as? You already found it. So it's negative x over 4y. Substitute that in where you see dy dx. Right? So you'll have negative 4y chilling out front in the first half of the numerator, plus x times 4, we'll call 4x, times your derivative dy dx. Oh, wait, we know what that is. We just found them like 18 minutes ago. That's negative x over 4y. And downstairs you got 16y squared. And at this point, you're almost done. The only thing I don't like about this is that we have a fraction as part of the numerator. And whenever we have a fraction as part of the numerator, how can we kill that? If the whole numerator were the fraction, we could get a common denominator, or more easily, I think, we can multiply by fancy 1. What's our fancy 1 here? 4y, because we got to kill off a little 4y denominator. We're going to multiply by 4y. So multiply there by fancy 1, 4y over 4y. When you multiply the 4y to the first half of the numerator, what's 4y times negative 4y? 16y squared. And then you multiply this to the second half of the numerator, and the 4y's cancel, and you're left with a negative 4x squared, right? Because you have 4x times negative x is negative 4x squared, and the 4y's cancel each other out, which is why we multiply by 4y as our fancy 1. And then in the denominator, what's 16y times 4y? 64y to the third. And then you could reduce that because everybody just divisible by 4. So you could finish this off and say, let's reduce the fraction, divide everybody by 4, and you get negative 4y squared minus 1x squared over 16y cubed. So the big trick with getting the second derivative when you're doing implicit differentiation is that almost always the second derivative will originally have a dy dx in it, because you'll have to probably differentiate a y thing as part of getting your second derivative. Don't forget, you know what dy dx is. You just found it. You had to find it in order to get to the second derivative goal. So you look back and say, wait, what is dy dx? Oh yeah, that's what it is. Plug that in, and then often you'll have to multiply by a fancy 1 to clean up the fraction of results. I think now we've done as much of that as we want to. Zelda?
If I was not doing like doing all of that, could I just like move it around so the y's on one side and all the other stuff's on the other side, like a normal differentiation?
Yeah, theoretically. That's more possible. But even with this, if you tried to isolate the y right off the bat, you would end up with a plus or minus because of the y squared. So if you subtract over the x squared, and then divide by 4, so you have y squared equals like 1 minus x squared over 4, and then you would have to square root both sides, right? So you'd end up with the square root of that thing, plus or minus up front. You tell me, would you rather do chain rule on this or just deal with implicit differentiation? Yeah, I think probably implicit differentiation would be less painful than dragging yourself through this guy's chain rule. So you're right. We could rewrite this. Now, not everything can be rewritten, but we could rewrite this and get y by itself and like write it in function notation and then just do normal differentiation. But that's not always an advantage. Any other comments, questions, follow up with example? That should have been example 4. Okay. They're a lively group this morning. All right, last couple things there. Just introducing chain rule to you guys with implicit differentiation. We haven't really looked at that yet. We've looked at some quotient rule now. We've looked at some product rule from last week. And we've looked at tangent lines to curves and finding where points of the tangent line are horizontal or vertical. But we haven't done any chain rule with implicit differentiation. And as soon as I find the remote, where'd the remote go? There it is. All right, so example 5. In order to differentiate the left side, what rule do we have to use? Chain, yeah. What's the inside part? X squared plus y squared. So that right there is your inner part. And then the outer part says 3 times the inside squared. So let's figure out dn. What's the derivative of that inside part? There you go. So 2x plus 2y and a dy dx because you differentiated a y thing directly. So all of that there is your dn. Then that multiplies d out, so times. D out is going to be what? 6 times the inside. So multiply the exponent down in front. 2 times 3 is 6. The inside is still x squared plus y squared. And now it's being raised to the 1 power, which I won't write. So it's the first. So this is d out. And that is, well, we'll come back to that. On the right side, 100xy. What rule for differentiation do you have to do here? It is the product rule. It's really easy to miss this product rule. It's really easy to just go, oh, 100xy. Differentiate the x, differentiate the y, done. But no, because the x and the y are multiplying, it's 100x times y. So do your product rule. You have a first part times the second part. And product rule says, what do we do first? All right, so first times derivative of the second. So first is 100x, and derivative of the second is dy dx. And then you add that to the second times the derivative of the first. So what's the derivative of the first? 100, and the second is y. So second times the derivative of the first is y times 100, which I'll just write as 100y. So that's your product rule. So this thing, make sure you product rule that job. Now the fun begins. We have to get dy dx by itself. Which means what do we have to do out on that left side? Foil it. You gotta foil it. Now maybe we can get away without like fully foiling. I kind of doubt it. So first of all, to make foiling go a little bit more smoothly, what can we do with the 6? I was going to say, like, distribute it from now. Now, if this were, like, a larger exponent, you'd have, like, 6, maybe that was, like, a 5. And you have number times something to the 4. So I would recommend that you distribute the 6 backwards through dn. Because you'll always be able to do that. So I'm going to distribute the 6 backwards through dn because there is possible that this x squared plus y squared stuff will have an exponent on it if it started off as like something times the inside to the 5th or the 4th or anything not squared. And then we'll still have just the x squared plus y squared bit here. And the right side is just going to kind of sit here and watch the show. So I'm not going to do anything on the right side for right now. So then you got to distribute this out. And you know what? Instead of like fully going totally distributing and saying like 12x times x squared and 12x times y squared and 12y dy dx times x squared and 12y dy dx times y squared, I don't recommend doing that. Because again, what if this were like x squared plus y squared to the something? You don't want to distribute that out, right? So we got to come up with a better way to distribute this out without going like all the way on it. So what I'm going to do is say take the 12x and distribute the 12x to the entire x squared plus y squared. And what I mean by that is I'm going to have 12x times the quantity x squared plus y squared. So I'm going to take each term here in the factor that has the dy dx and kind of just multiply it to the front of this other factor, but not really distribute it through. So 12x is multiplying all this stuff, but I don't really do it. And the 12y dy dx is multiplying all this stuff. But again, don't really do it. Just kind of say, hey, these guys are multiplying. And that way you've kind of broken it apart into two separate terms, and you now have a way to get dy dx by itself, but you don't have to figure out what is all the stuff did you distribute out to. Because again, if this were x squared plus y squared to the fourth originally, and then you had x squared plus y squared to the third, you don't want to go all crazy distributing that out. You'd rather just write it like this and have terms that involve like many factors. Over here, just copy and paste. I have 100x dy dx plus 100y. Now, at this point, you kind of do your prisoner swap. So everybody with a dy dx gets over to the left. Everybody without a dy dx gets over to the right. And you can just pick up this entire 12x quantity x squared plus y squared term and move it over here. And because this whole thing is positive, because there's a positive 12x up front, when you move it over here, just slap a negative in front of it. So we'll have a 12y dy dx quantity x squared plus y squared. We'll minus over the 100x dy dx. That all the dy dx things are on the same side. And over here we have a 100y. And then we'll subtract over that entire 12x quantity x squared plus y squared business. So instead of like doing nice small terms like 5xy or 3x squared, you have a term that's big ugly like this, but that's better than distributing the whole thing out. Now that you have everybody dy dx on the same side, what can you pull out of that? Dy dx. Now you might look at that and say, I'm pretty sure the GCF is bigger than just dy dx. I think 12 and 100 also have a GCF of like 4. So we don't care. We don't care. We just want to get the dy dx by itself. So pull out the dy dx, and everything else stays as is. So we have 12y multiplying an x squared plus y squared, and then we're minusing 100x. And again, you could distribute out the 12y and the x squared plus y squared, but that's only in this particular scenario because the x squared plus y squared doesn't really have an x bound there. But other times it will, so get used to writing it like this. It's going to be less annoying this way. And then you can divide that whole thing over here. So we'll divide that whole thing in the brackets over here to this right side. On the right side, where numerator is 100y minus 12x quantity x squared plus y squared. And the denominator is 12y quantity x squared plus y squared minus 100x. Now, you can simplify this fraction either correctly or not correctly. The temptation is to do it wrong, because some people are going to see, oh, x squared plus y squared at the top and x squared plus y squared at the bottom, let's cancel them. But we're not allowed to, because why not? Is this x squared plus y squared multiplying the entirety of the numerator? No, so it's not really a factor of the whole numerator. Similarly, is this x squared plus y squared downstairs multiplying the entire denominator? No, it's only multiplying part of the denominator, so it's not a factor to the whole denominator. You can only cancel out factors that are factors of the whole top and the whole bottom. This is just part of one term. This is just part of one term. You can't cancel out terms or parts of terms. You can only cancel out factors of the whole thing. So don't cancel those out. But what is a factor? What number is a factor of the entire numerator and of the entire denominator? 4. Like, you can divide the 100 and the 12 and the 12 and the 100 by 4. So you can divide the whole thing by 4. And if you do that, you end up with 25y minus 3x quantity x squared plus y squared over 3y quantity x squared plus y squared minus 25x. And that's your final simplified derivative. If you get to here and you leave it like this, I'm going to say that's pretty damn good. Good job. I am not going to take off points if you don't go to this very last step and simplify it all the way. If you distributed out the 12x and the 12y through the x squared plus y squared, more power to you. But again, that's not always going to be a feasible option because, like, kind of going back through here, what if this was x squared plus y squared to the fifth? And then this 6 is really a 15, and then this is to the 4th. You really cannot distribute this out in any feasible way, and that whole thing is getting raised to the 4th power. So you're just going to, in that case, leave it like that. So that's why I didn't distribute through the 12x. This would also be to the 4th. You just say, hey, take this d in stuff, and that would be like 30x plus 30y, and multiply each of these terms to this thing by just slapping it to the front of the x squared plus y squared. But don't really like go crazy multiplying it all out. That's all. That's probably like the worst case scenario. That's not true. I could make this much worse. I could make this worse by making the inside a product. But I don't plan to do that to you. So that's about as bad as things are going to get for us with implicit differentiation. You guys have any follow-up questions with example 5? There's a lot there, right? Fun. So your quiz on what I think is going to be Thursday, but it could be Friday, is going to be wrong class. All right, I'll try to do this from memory. It's going to be like 4, here's an equation, give me the derivative, go, with implicit. And a couple of them will be pretty straightforward, like example 4. And then you might have like a product rule and or a quotient rule and or a chain rule thrown in there as like the other 2 problems. And then on the second page, that'll be stuff like what we did over here in example 4, where we say, here's an equation, here's a point, give me the equation of the tangent line. Give me the equation of the normal line. And that'll be the second page. And then maybe also give me the second derivative. And then the third page will be kind of along these lines of here's an equation, tell me where the tangent line is horizontal. Or tell me where the tangent line is vertical. And that'll be the whole quiz. So it'll be less than your last quiz test thing in terms of the number of things that you have to do. Same number of pages, but more spaced out. So that's what you have to look forward to on hopefully Thursday. Any questions? All right. One last thing to gather here. Sine of x plus y over equals 4y. Left side, what rule do we need? Chain rule. We got an outside and inside. Inside part is this x plus y. What's the derivative of x plus y? 1 plus dy dx. So that is dn. What is the derivative of sine? Cosine. What is inside our cosine function? X plus y. All your trig functions are fair game for Thursday. So if this were like a tangent function, this would be secant squared of x plus y. If this were a cosine function, then this would be negative sine of x plus y. And just make sure you keep the multiplication, don't turn it into subtraction by accident. But the derivative of sine is cosine, and the inside of that is still x plus y, so that's d out. And over here, what's the derivative of 4y? 40y dx. Now, on the left side, what do we need to do? FOIL, or distribute. So when we distribute this out, we have 1 times the cosine function. What's that? The cosine function of x plus y. And then you have dy dx times the cosine function. What's that going to be? Yeah, dy dx cosine of x plus y. So you distribute the 1 to the cosine, you have the cosine function. Distribute the dy dx to the cosine, you have dy dx times the cosine function. Over here, he's just watching the show. Yes?
Does it matter if the dy dx goes before or after cosine?
It doesn't, but I prefer to put it in front because anything that goes behind, the temptation is then to put it inside the cosine function. But if you can just make sure that the dy dx is outside and cannot get inside, it's fine. Now, what's our next step? Isolate dy dx stuff. So get all the dy dx's to the same side. In this case, because I already have dy dx on the right, I'm going to bring them all over to the right because I've only got a single non-dy dx term. So I'll subtract over the dy dx cosine of x plus y stuff. And then what can you do with this? Factor out that dy dx that we want to isolate so that you're down to a single dy dx thing. And then finally, divide. And what's your fraction look like? What's our numerator? Cosine of x plus y. And what's the denominator? Minus cosine of x plus y. And are you allowed to divide these cosines and turn it into 1/4? No, please don't. Because the denominator, cosine, is not a factor of the whole denominator. It's just a term. So you cannot say, boom, cancel those out, make it 1/4. That's not allowed. That would be illegal canceling out stuff. So this is done. That's it. So that's just pure chain rule with the sine function and no other special trig derivative rules, no power rule over here, product rule looking for y because there's no x multiplied to that, and then you isolate the dy dx. And I think that pretty much now covers all of our bases. So if you're not going to be here tomorrow, you've seen everything that we're going to kind of get through with this. You've seen finding points with the tangent line is horizontal and finding points with the tangent line is vertical and writing the equation of the tangent line to the curve at a point and finding a second derivative and using chain rule with implicit differentiation and seeing trig functions in conjunction with implicit differentiation and seeing product rule and seeing quotient rule. So you've seen all the things there are to see with implicit differentiation. So you're ready for your quiz. Well, maybe not. So your homework from Friday is due tomorrow. You'll have another homework due Wednesday. And then I have a worksheet of just extra practice finding derivatives and finding second derivatives with implicit differentiation. And there's an answer key to that posted in the folder for this week. So at the top of the folder for this week, there's this worksheet and its answer key that you guys can look at for extra practice if you don't have enough on your plate already. Here you go.
Wait, is the key on there?
The key is not on here now, but the key is on Schoology. Sorry, Prince. I'm not like the physics teachers with the key directly on their worksheets.
No. For APR science, key to the worksheets.
He doesn't? He does.
It's like, we have practical sheets, but like, there's no answer.
That's because it's environmental. They're not hard and right science. It's environmental science. That's why the climate's destroyed, right? So. Is this an extra?
Yes.
All right, thanks. All right, so you guys can work on this. You can work on your homework that's due tomorrow. You can work on the homework that's due on Wednesday. That's the day, Wednesday. You can do any of those. As you're working on it, it's your chance to be able to ask me questions if you get stuck on something. This is just for fun. Yeah, this is just extra practice. If you get done the 2 homeworks and you're like, you know what I need in my life? More implicit differentiation. Here you go. Brian, if you get bored catching for Zupedo today, you can like Hold
I'm
on.
not throwing them today.
Yeah, you're not
Just
throwing
them
it
over Marion.
Okay.
on Wednesday.
Okay, cool. So, whoever you're catching today, I guess not Zapito probably has less control from what I hear, because he seems to be pretty good.
Yeah, but you can't blink.
No.
or else you got hit.